All right, hello, this is Mr. McMurray, and this is the first session of Notes, Biochemistry Notes. We're talking with the inorganic compounds we're going to talk about. We'll talk a little bit about what that means today. So, here's the deal. As I go over these, you need to write down, certainly anything I write down on here definitely needs to be written down, but I would recommend that you write more than that, probably. Some of the other stuff that we talk about and draw pictures of, you need that also. All right, so this is Biochemistry Notes. If you want to call it that, up at the top, you can do that. All right. Bio just means living things, and chemistry means has to do with chemicals. So these are the chemicals that are important in living things. All right. And in order to talk about that, we need to first talk about the difference between organic versus inorganic. All right. And we're going to talk about inorganic first. So I'm going to go ahead and put that up here as our first point. But what is the difference? Well, organic, if you're talking at the grocery store and you see the word organic, it means that it was grown without any chemicals, man-made chemicals applied to it, or pesticides and things like that. Fertilizers, what have you, been added to it, weed killers, whatever. And that is not what it means in chemistry. When we're talking about in chemistry, organic or inorganic have to do with, are they made by living things or not? All right. So inorganic, not organic, then means they are compounds not produced by living things. All right. So not produced by living things. They're in living. In means not. So they're not organic. They're not produced by living things. They are just there otherwise. Now, one of the main ingredients that things have, if you burn something like a piece of paper, it came from a tree or a living thing, you will have black ashes. Those black ashes that are left are carbon. All living things contain carbon, and so organic compounds contain carbon. Guess what? Inorganic do not contain carbon. Okay? There will be one important exception that we'll talk about, but in general, they do not contain carbon. All right. If you burn them, they may or may not leave black ashes behind because they don't have carbon in them, and usually that black ash left behind is the carbon. All right. Generally speaking, they are relatively simple structures. Okay. I'm going to put this as B here. All right. They are relatively simple compounds, okay, inorganic. All right, and so they're fairly short and simple. Salt, for example, NaCl, sodium chloride, that's pretty simple. You have one atom of sodium, one atom of chlorine, nothing very complicated about that. Okay, you might have something a little more complicated like calcium phosphate, and this would even have parentheses, and this would have a 3. Okay, Ca3PO4, Ca is calcium, so you have 3 atoms of that. 1 phosphorus times the 2 out here makes 2 phosphoruses. 4 oxygens times the 2 makes a total of 8 oxygens. Okay, that's a little more complicated, and that's a total of about 13 atoms. That's pretty big. But when we talk about organic, things that are in your body, you may have thousands of atoms joined together in a long chain to make a starch or a protein or something like that. So inorganic chemicals are very simple. A lot of times people look at the ingredients on the food they eat and say, oh, I don't like those big names I can't pronounce. Well, take an orange, for example, or banana. If you listed all the ingredients in it, there would be some really big, long, complicated names that have thousands of chemicals in them. So just because something has a big name does not make it good or bad. It is more likely to be inorganic if it's small, and it's more likely to be organic, which means produced by a living thing, and therefore could be natural. If it has a big, long, complicated name. So just because something has a short name doesn't make it safer. All right. Nor does being inorganic necessarily mean it's bad, anything about it. In fact, living things need inorganic compounds as well as organic ones. All right. Now, what we'd like to look at now are, I guess you could put this as C here. There are 3 main inorganic compounds. It's been a long summer, I guess. All right, inorganic compounds. All right, that are used and are important to human beings and all living things for that matter too. Now there are many, many, many different kinds of inorganic compounds. Okay, that's not all of them, but these are 3 main ones that are important to us. Number 1 is water, or H2O. Or if you wanted to write it, you could also write OH, which is still 2 hydrogens, 1 oxygen, same thing as that. But anyhow, that is water. Okay, now water is important. Well, duh, okay, but let's talk about some of the ways that water is important. In fact, most of our inorganic compounds are going to circle around water. Okay, first thing is, it is a polar molecule, or it has polarity, and I'm going to put it along with that, it is a solvent, because those two things kind of go together. The fact that it has a polar is that it also allows it to be a solvent. In fact, water is sometimes called the universal solvent. Now, universal means everything in the world will dissolve in it. Will everything in the world dissolve in water? No. So it's not a universal solvent, but it is by far the most common thing that things are dissolved in. Okay, and when we have a liquid we use to dissolve things, it is called a solvent. All right, but let's talk about those two things first. What does it mean to be polarity? Well, we have a pole. All right, we know the North Pole and South Pole. They come in pairs. A magnet has a North and South Pole. All right, and that's basically what we're saying here. Okay, water has a positive and a negative pole. Okay, we said it's made of one big O oxygen atom. So I'm going to put an O there for oxygen. And then it has two little tiny hydrogen atoms stuck on it. All right. So even though there's two hydrogens, they're really the smaller part of it. And if you turn it around, put the ears on top, it looks like Mickey Mouse kind of, or a little bear or something. But anyhow, now there are two electrons here that are supposed to be shared. An electron here, and let's say an electron over here. Okay, and they're supposed to be shared between the oxygen and the hydrogen. Half the time they go around the oxygen, half the time they go around the hydrogen, and same thing over here. But this is kind of like if you go to a sandbox with a bunch of toys with little kids, and you have one big kid and two little kids. Guess who gets to share the toys most of the time? Well, yeah, that's right, the big kid, because he can get his way. Well, same thing happens here. The oxygen keeps those electrons over here most of the time and doesn't let the hydrogens have them very often. So most of the time, this side of the top side up here where the oxygens are, this side of the molecule tends to be a little more positive because electrons have a negative charge. And so this side tends to be there. Since the hydrogens, they need that electron to be neutral, but now they've lost those negatives, that makes them more positive. So you have two poles to water. You have a negative pole up here by the oxygen side, and you have a positive pole down here where the hydrogens are. And that's why we say it has polarity. Instead of being nice, even, neutral atom where there's no charge at all, which a lot of compounds are, this one actually is negative on one side and positive on the other side. All right, it has two poles, and that's why it's called to be a polar molecule. Now, if we stick something like salt in there, we have a positive sodium and a negative chlorine. And when they are joined together, they're neutral. They're happy together. But when you stick them in water, something happens. This positive sodium says, well, I could join up with this negative chlorine, but I've been with chlorine for a long time. I think I'll go over here and hang out with the negative oxygen. Okay, and kind of breaks it off with chlorine over here. And the chlorine says, well, fine, if you're going to do that, I can do the same thing. So I'm going to go over here, and I'm going to hang out with the hydrogens. They're positive. You're not the only positive fish in the sea. And so it hangs out over here. And when salt dissolves in water, that's what's happening. The sodiums are going to one side of the water molecule, the chlorines are going to the other side, and it makes it look like the salt disappears. Now, it's still salt. If you taste the water, it's salty water. But that's why it dissolves so well in water, because it separates into these separate sides. And so water is a polar molecule. Okay, it has these two positive and negative poles. In fact, you could say it's bipolar, but it doesn't have to take medicine for it. It's okay. All right, it's the normal way it does. Okay, and why this is important is because this allows other chemicals, which are called solutes, to dissolve. All right, so it allows those things to dissolve in water, and that's why we said water is a good solvent. Okay, now let me erase some of this. All right. Now these other chemicals that dissolve in the water are called solutes. So the solutes dissolve in water, which is the solvent, remember, okay, to make solutions. All right. And hopefully I will have a chance to make the flare demonstration and tape that and put it on the webpage. But basically, if you mix dry chemicals together, a lot of chemicals wouldn't do anything. They just sit there. Okay. In order for them to react, they need to be in a solution, in a liquid. And then when you mix the liquids together, they will do all kinds of neat reactions. Okay. So very important that things be able to dissolve in water, because that allows them to make solutions, and it allows the chemicals, or the solutes, to react with each other. All right, and they couldn't react with each other if they didn't have that property of water that allowed them to dissolve. If they're just mixing solid chemicals together, nothing happens. All right. Now, not everything, we said this was A, about water being polar and a solvent and all that, not everything can dissolve. Some particles are either too big, or they just will not break down, okay? So, but still, they can float in the water or get carried along with the water, okay? So chemicals that do not dissolve, all right, chemicals that do not dissolve, or they're just too large, can form, they float in the water and they can form what we call colloids or suspensions. All right. All right. Now, once again, I may have a chance to take a short video of an example of this. If you have a jar of muddy water like this, okay, and you shake it up, then the whole thing is going to have dirt settled all over the place, okay? All right. But if you let it sit long enough, over time, eventually all the mud will settle down the bottom, and you will have clear water up here. Okay, now the biggest particles will settle out first, sand, gravel, things like that, and then gradually clay and the little tiny floaty stuff will settle down. Some bodies of water, like a stock pond, tank, whatever, or a river, a lot of the rivers around here have real fine mud in it, clay type stuff, and they always look muddy. Why? Because any movement at all is just enough to keep that stuff from settling out. Okay, well, here's the deal. A suspension is when stuff will settle. All right, if something settles out eventually, then that is an example of a suspension. Okay, they're suspended until they settle down. All right, kind of like if you get sent out to ISS, I guess you get suspended until you settle down because you did something you shouldn't have done. Okay, colloids, on the other hand, never settle. All right, you hear people say, we never settle. Well, these are those kind of people. Colloids never settle. For example, Jello, a chunk of Jello, gelatin blocks, whatever, is a suspension of a liquid in a solid, but it stays pretty much together. Over time, a little bit of the liquid will come out and it gets kind of runny a little bit, but for the most part, it stays suspended. Okay, milk has been homogenized. When they stir it all up so it'll stay suspended, you don't want all the fat and the yucky stuff to settle down to the bottom. Usually that's a sign that there's bacteria in there eating and digesting your milk. You don't want the milk to settle out. If you have clear watery stuff on top and the white creamy stuff on the bottom, that would not be very good. You want it to all stay mixed together, and so that would be more of an example like a colloid. All right. And it looks like we have about 30 seconds left, so we'll kind of stop right there. Next time we'll pick up with water, talking about movement, how it allows things to move around in organisms. All right, so don't forget to tune back in to the next exciting episode of Inorganic Notes.